Uttam Prabha. Digital India. Educated India.
Welcome to the course Introduction to Algorithms. My name is Saurabh Mukhopadhyay. I am a faculty member at IIT Kharagpur. I am lecturing this course. In this lecture, we will cover two techniques for graph search, that is exploring the graph, namely the breadth first search and the depth first search, BFS and DFS. So, let us start with the, first part we will cover the BFS or breadth first search, and the second half of this lecture will cover the depth first search of the DFS. So, let us start the graph search technique. So, what do you mean by graph search? We want to explore the graph. Exploring means say given a vertex S, we want to see what are the vertexes are reachable from S, or we want to find a path from S to any other vertex S to a vertex T, or we want to find all the vertices which are reachable from S, from the given vertex. So, these are called exploring, these are all the graph search technique. Okay. Basically, they are explore a graph, that is find a path from a vertex S to a vertex T, or we want to see whether we can from a vertex S we can reach to another vertex, that is also given. So, that is also a exploring, or we want to see, we want to visit all the vertices which are reachable from S, all the vertices which are reachable from S. So, basically we want to explore this, exploring the graph. So, that is called graph search. Now, what is the use of this? I mean, why we are, so what are the application for this graph search or exploring the graph? So, application of graph search are mainly say web crawling. So, Google. So, everybody is, suppose everybody open a new web page and want to index. So, what Google does? Google does the exploring the graph like breadth first search or BFS to from the existing page you want to reach to all the pages which are reachable from there. So, that is the technique Google use for web crawling, for BFS technique or the breadth first search technique use. And another is social networking, the Facebook. So, we want to find the friends of friends to invite or some. So, basically say two labels. So, this is the, so basically we want to find the friends of friends. So, this is one label, then two labels. So, slowly we have to explore it. I mean, we have to search it, like first level we can reach to the all the friends which are friends of S, direct friend, and then from that we can reach to the next level friends. So, friends of friends. So, level wise we can do this, that is the social networking, Facebook. Another example could be network broadcast. Suppose we have a network internet or Ethernet and we want to broadcast a packet, we want to do the data out. So, we need to reach to the all the nodes of the in the network. So, that is also a exploring application, like we have to search in a graph, okay, to reach out to do the data out for the we have to do the packet reachable to the all the nodes. And the next application is garbage collection. This is the most of the current modern language has this facility for the garbage collection. So, basically if we allocate some memory, like in C language we do the malloc or calloc. So, there we allocate some memory dynamically. So, unless we free it, so earlier stage we used to free this. I mean, we have a free call to free this, so that if we are not using it, it should be free to use by the others. Now for the modern language, like for second version of the C, also Python, all the language have this garbage collection. We don't need to free it. So, that will be done by the language itself. So, what they do, they just do this graph search. So, So whatever the existing variable, the current variable they are using, so from that variable they will see whether they can reach to the all other variables. So whichever variable is not in use, so that they will free it. So that is called garbage collection. So all the modern language is having this facility, garbage collection. There they use the breadth first search. So they see whether it reachable from this, I mean the current variable we are using. Otherwise it will free the memory, free the variables to reuse. And next one is the solving puzzles or games. So we will discuss the one puzzle like Rubik cube or the pocket cube, and then how we can solve it by using the graph search, how we can view this as a graph, and then how to reach to the solved state. So that is the another application. So there are many applications on this. So let us first talk about, now let us concentrate on the Rubik cube or the pocket cube. So consider a 2 by 2 by 2 Rubik cube. It's like this. We have all seen this pocket cube. Now this is having, so how we can see this as a graph? I mean, so every position if we consider as a node of a graph. So how to configure a graph? So what we do, vertex of each position of the state of this cube is a vertex, like this is a vertex. Now if you do the one change like 90 degree in any direction, that will give us another positions, and that will be the another vertex like this. So and edges, basically when you do the one change, I mean 90 degree turn like this or this, so any direction, so that will be the edges. So from this state we can go to this state like this. So that is the edge of, so this is a directed graph, sorry, undirected graph. So it is basically reversible. So from that also we can go to the previous state, because we just made one move. One move means this is the position, say this is a state. Now any direction we can do this changes in 90 degree turn, and that will be the another state, and from that state, from this state to that state we can reach by just one move, and there is a edge, and that edge is reversible. So from again the reverse move we can reach to here. So that is the basically edge of the graph. So this is the graph we can consider, and this is undirected, as I said, because moves are reversible, because from this if we make a move 90 degree turn, we reach to the another state, that is the edge, and from that state we can again by the reverse of that turn we can go back to this. So this is a undirected graph. Okay. Now how this we can use this for solving this? So there is a solved state of this. So basically we will see this is nothing but we can view this as a the level wise, that is called breadth first search. So we explore the graph level by level from a state S. So that for Rubik cube, that state is the solved state, and we label that state as 0 level, and then the vertex reachable from the from I minus 1 to I. So that, so for next is one level means which are reachable from this 0 level vertex. So that is one level. So in general, level I means vertex reachable by a path of I edges but not fewer. So that means level by level it is. So we will come to this example, and we build level I greater than 0 from level I minus 1 by trying all the outgoing edges but ignoring the vertices from the previous level. So let us do this exercise on this Rubik cube or the pocket cube. Suppose this is the solved state. Okay, I mean that all the colors are matching, so that is the solved state, because every position is a state. So that will be also state. Vertex. So that is the solved state vertex. So from there we can just consider all the states which we can reach by just one move. So, if it is a Rubik cube, then it is just a just 90-degree turn from that state, from the solved state, one move, just one move. And in general, it is we start from a state, we start from a vertex, that is the starting vertex S, and from there that is of level 0, and from there just the direct edge, all the vertices are basically our level 1 vertex and next level vertex. And then again from there we consider all the direct edge which will be in the next level vertex. So, that these are the vertices are in the level 2. If this is level 0, this is level 1, this is level 2. This is the way we explore the graph, and this technique is called breadth first search. The way we are exploring is called breadth first search, or the BFS. Okay, so we continue like this from this level we take. So, this is the say ith level. So, for how to reach to the I plus 1th level. So, we take all the vertices at the ith level. Now, we explore all the edges and we see what are the vertices are reachable from this level. So, that way we continue, and finally, we reach to this, and this is for the Rubik cube. We consider this is level 0, level 1, level 2, and this is the last level. So, these are basically so for Rubik cube, this is from this path to this path. So, any vertex will be in this, any position of the Rubik cube will be one of the vertex in this search, I mean in this level wise breakup. Now, we do not know where, because these are exponential growing. I mean this is exponential size after some point of time, very difficult to maintain. But this dimension, this is called dimension, or the God number. So, this is not much. So, for 2 by 2 by 2 it is I think 11, we will come to that. So, this is God number, this dimension of this. So, that means what is the meaning of that? If it is 11, that means if we are in any state, so that will be one of this vertex over here. So, from that we can reach to the solved state by less than or equal to 11 move, if we know this breadth first search technique. But only thing, to locate that vertex it is difficult, because this is exponential growth, like number of vertices over here. We will see what is the number of vertices over here. So, this is basically BFS, or the breadth first search. We do the searching level by level, starting with the starting vertex as a 0 level vertex, and then we consider all the vertices which are reachable from this level. They are level 1, they are labeled as level 1 vertex, and we consider the next level which are reachable from this level 2 vertex. So, if we consider the Rubik cube, this is the solved state, and these are all the position, all the state of the position of the cube which are just one move from the solved state. So, that means just 90-degree turn from the solved state. So, if we are here any of the state, we should be able to reach to the solved state just by one move. I mean, if we are good player, I mean if we do this breadth first search. Now, again these are the level 2. So, if our cube is in this level vertex, then from here we should reach to the solved state just by the 2 move. So, that is the idea. So, and this dimension is basically called God number. Now, this dimension is 11 if it is 2 by 2 by 2 Rubik cube, and it is 20 if it is 3 by 3 by 3 Rubik cube. So, theoretically, so it does not matter where we are. So, it should be, we should be able to solve the Rubik cube, say 3 by 3 by 3 Rubik cube in at most 20 moves. So, because this is the will be somewhere here. So, for 3 by 3 by 3 Rubik cube, this length is this is called God number, this length is 20. So, we should be able to solve the Rubik cube in 20 move maximum. Okay, and in general this is a result which is for n by n by n Rubik cube. This is bounded by n square by log n. Okay. Now, you may be interested to know how many vertices are there in that graph just for 2 by 2 by 2 Rubik cube. So, this is the number, huge number. Why this is this? Because if you just take a cubelet, okay, just take a cubelet. So, for there are how many cubelets are there? 8 factorial cubelets are there. Okay, and each position we have 3 to the power 8 comes from each cubelet. So, it is basically 8. So, that is sorry 3 position of the twist, either this way or this way or this way. So, 3 possible twist, and it is 8. So, it is that's why it is 3 to the power 8. And how many such cubelet? A factorial a. So, factorial 8 into 3 to the power 8. So, this number is huge. So, this many states are there in the just 2 by 2 by 2 Rubik cube. So, that means in this so there are that many vertices are there. So, that means these are exponential growing. I mean, although this length is 11, but this size is exponential, it is difficult to maintain. Okay. But this length is 11. So, for 2 by 2 by 2 Rubik cube. So, wherever we are, we should able to reach to the solved state just by 11 move. So, that is the that is the BFS or breadth first search. Okay, now come to the pseudo code for BFS. So, this is the vertices. V is the set of vertices, and this is the graph. Graph is given in the adjacency list. So, the input is a graph G, which is V cross E, and we have given the graph in a adjacency list way. So, this is the adjacency list. So, that means we have a list for each of the vertices. So, we have a adjacency list of each of vertices V1, V2 like this, and we have a linked list over here which are connected with, I mean which are the vertices are in the V1. So, like that. So, that is the degree of V1. Okay. Now, what to do? And we have another input which is called the starting vertex. We have given a starting vertex to start the search. I mean start to explore this graph. So, that we put the level of that vertex to be 0, and the parent of that vertex is null, because that is the starting vertex. So, first vertex to start. So, parent is null. So, this is a Python code. You may be familiar with this pseudo code. This is not a pseudo code. This is similar to Python. This is a Python code basically. Okay. So, now we are putting this label of S to be. So, this is a level by level search. Okay. Now, we go to the next level. I is 1. So, after this 0th level, now we put the frontier which is S initialize, and now why frontier is not empty, because this is S, so it is not empty. We put next to be empty, we start with, and then we take a node from in the frontier set. So, that is the first node S, because initially this is S. So, that is our U. Now, we consider all the nodes which are adjacent with this. Okay. So, we consider, so this is our U, and we consider all the vertices which are in, so these are the all vertices which are in adjacency list of U. Now, U is labeled by I mean initialized by 0. If it is S, then this is labeled by 0. Now, we consider all the vertices which are adjacency list of this node, which are in the adjacency list of this node. Now, if V is not labeled, so this is one of the V in the adjacency list. So, this is V. Now, if V is not labeled, then only we do the labeling on V. If V is not labeled, then only we label the V by I, because earlier label is I minus 1, and the parent of V we put to be u, because this is the direct edge. So, parent of v will be u. Why we need the parent? Because we want to find the shortest path also. So, this parent link will give us the shortest path. We will come to that. Okay. And we add this v into this next set. So, we append this v into next set. So, this is the next level node and we append this and this will continue for all the adjacency vertex of u. So, we do it for all these v's and we put everything in the next set. Okay. And this all these vertex are labeled by basically the I. Okay. And now after this loop we make the frontier to be next, because we take the next level vertices and we increase the level by 1. So, now it is I plus 1, I is equal to I plus 1, and then we continue here. If frontier is not empty, then we do the same thing. We consider these are our, we take a vertex from this frontier, then we consider all the vertices which are adjacency list of this, we label them by the next level, that is I plus 1, and we make the parent pointer also to have the shortest path. So, this way we continue, and this is the again for the next that level we increase we add the node into the next by this next append. So, that is the way. So, let us take an example. Okay. Suppose this is these are the vertices and these are the edges of a graph, and we want to do the BFS or breadth first search on this graph. So, let us start with the this is the first. So, first this is also part of the input. We have given a source vertex to start the search. Okay. So, this we put the label 0. We put this vertex label 0, and the parent of this is null, because this is the starting vertex. Now, we consider all the vertices which are adjacency list of this vertex. So, this is A and X. So, we took this vertex as V. So, this is U. Now, this will make the label 1, and we can have a pointer over here to indicate the parent of this node. Okay. And similarly, this also we can have a pointer over here to indicate that this parent of X is this node. And then we have a this is our so we put these two vertices into the next, and next will be the next frontier. So, these two we put it into the next, and this will be our next frontier, and then from this will be next frontier, and we take the vertex, we take a vertex from this A, and then we check all the vertices which are connected with this degree, the adjacency list of A. So, this is the vertex, we label this vertex as the next level 2, and we can have parent, we have to use the parent pointer. So, parent pointer of this jet is A, and similarly we have this vertex. Yeah, similarly for this we have these two, just a minute. So, similarly for this vertex, what are the in the vertices in the adjacency list? This one, but this is already labeled, so we don't need to worry about that. So, these two are not labeled. So, we take this vertex, this is not labeled. So, we have to label that. Label will be the this is label 1. So, this will be label 2. Similarly, this vertex, and we have a parent pointer also. So, the parent of this vertex is this one, and parent of this vertex is this one, and we put these 3 vertex into that next set, and the frontier will be the next, and the label I will be I plus 1. So, label is now 2, and the next label will be 3, and the frontier is this 3 node Z, D, C. Now, we check all the vertices which are in the adjacency list of this vertex. Okay. So, this is level wise, level by level searching. So, now for this vertex, this is the node which are in the adjacency, but this is already done. this is already labeled. Now for this vertex, these two, so now we can label this as a 3 and this is already done, and for this vertex, if it is already labeled by this, if we first, then we will not, I mean this is done, and then we check this one, this will be done. So label 3, so these are the level 3 vertices. Okay, done. And we can we add the parent pointer over here to indicate. So the way, I mean this is the this is parent pointer of this vertex, and this one, which way we are, I mean if we are following this, I mean if this made this label change, then this one, otherwise I mean this one, depending on which one made this change. Okay, so now this is the variable. So frontier is initialized by s, and then the next frontier is the next level, next frontier will be the next, I mean next set, and that is ax, which is the level 1 vertex, and then the next frontier is z dc, which are the level 2 vertex, and next frontier is this one, which is level 3 vertex, and we are done. So this is this way we label the vertex. Okay, and this parent pointer, what it will give us? It will give us the shortest path from S to that node, because from F, if we follow this parent pointer, we come here, then we follow the parent pointer, and then with this. So this reverse way, it will give us the, for shortest path we need to have a directed graph. So this will work for the directed graph also. You have a direction. So if we have a direction like this, so we follow the parent pointer this way, and then we follow the original direction from S to this node. So from S to this node, this is the shortest path. So there is no edge weight over here. Edge weight we can say 1. So this is the shortest path from S to this node. So these parent pointers will give us the shortest path. Now let us talk about the time complexity of this code. Okay, so now how much time we are doing here? So we have a loop over there, which is of size adjacent the degree of v basically for each v. So that is the summation of, this is the time for summation of this thing, because if you come to the code, sorry, yeah, so this is this size. So this is, we are doing this we are visiting all the vertices, so that will be order of v plus, and here we have a loop of size summation of degree of v, and that is basically by Hansek's lemma, this is order of e. I mean if it is directed graph, it is undirected graph, it is 2e, otherwise it is e. So let us come to the analysis part. Yeah, so this is the order of e. So it is, time is basically order of e plus v plus e, because we need to see all the vertices. We are reaching to all the vertices, so that's why it is v plus e. So this is the time complexity for breadth first search. And as an application, we said the shortest path one. So that if we follow the parent pointers, it will give us the, for every vertex v, the fewest edge to get from S to V, that is the shortest path. We can say this is, if we put the weight of each edge is 1, so that is nothing but the shortest path. So basically we follow the parent pointer. So S is S is from S, I mean from V to, sorry, from V to this, yeah, so we just follow the parent pointer of this. So v, we go to the parent, of v, this link, and then we go to the parent of v, and it will reach to the s, and then if we follow this path, and this will give us a shortest path, the other way around. Okay, so this is one application of this. So next we will start the another search technique, which is called DFS, or the depth first search. Okay, in the depth first search or DFS, what we do, we will explore all the vertices of the graph. So, unlike BFS which we have discussed already, so it was explore all the vertices which are reachable from the source vertex S, and it is level by level search, and it is good for finding the shortest path from that source vertex to all other vertices. But this exploring is for all the vertices which are reachable from the source vertex. But here in the depth first search, we want to explore the whole graph. So, that means we want to reach out to all the vertices, not only the vertices which are from the given source vertex. So, we want to explore whole graph. So, that is the idea. So, it is basically the idea is like exploring a maze. So, it is like we start from a position and we follow the path until we stuck, and once we stuck, then we backtrack, we come back to the previous position and we take the, so we should have a memory. So, we come back to the position and we take the other path from that position and we follow the path until we struck. Once we stuck, then we do the backtracking and then we come back to the position, previous position, and we take the another path from that position. So, like this we do. So, this is basically the idea is to follow the path until we stuck, and once we stuck we will do the backtracking along with the path, and then so this can be very nicely done in computer by the recursive call, recursive exploring. Only thing we need to take care of the repetitions. So, we should not repeat the vertex which you already explored. So, there should be a pointer to avoid the repetition. So, that is the so we should not repeat the vertex. So, we should see the vertex once, and then that is the things. So, this is the, now let us come to the how we can do that. So, let us discuss the pseudocode for this DFS. Okay. Now, this is the code for DFS visit from a source vertex S, and this code we will use for the original DFS visit algorithm. So, what are the input? Input is the graph. We have given the adjacency list of all the vertices, and this is the vertex set, and this is the adjacency list of the vertices, and this is a source vertex. We want to explore the graph. We want to explore the graph which are reachable from this source vertex. So, this code will does that. So, this code is the this code will be exploring all the vertices which are reachable from the source vertex. So, what is this code? This code is a recursive call. So, we follow the path until we stuck, kind of thing. So, what is the recursive call? So, this is our S vertex, and there are some other vertices which are in the adjacency list of this. So, one such vertex is say V. Okay. So, one such vertex is V. Now, we check whether V is already explored or not. So, that checking is done by this step. If V the parent pointer is used for that avoid the repetition, we will use the parent pointer. So, if V is not in parent, so that means V is not explored earlier. So, we have to avoid the repetition of the vertices. So, parent pointer of S is said to be null. So, S has started to, this is the starting of exploring S, and then this from V we call this same BFS visit on this V. So, what it will do? So, it will first set the point of V as S. So, that is the pointer. So, the parent of V is S because the V came from S, and then once we call this recursive call of the same DFS visit on V, so it will check the vertices which are in the adjacency list of this, and then it will again call this. So, if there is no more vertex to go, if the path ends, then we will come back to the previous position, and that will be taken care by this recursive call. We can have a while loop also here, that will be taken care of by the recursive call. We check whether any other path from V are there or not. If not, we will come back to S. We explore the other path from S, other vertex. We explore, keep on going until we stuck. Once we stuck, we come back like this. So, this is the code to explore all the vertices which are reachable from S. Okay. All the vertices we have explored which are reachable from X once we complete this. And we have to be careful by not repeating the vertex which has already seen. So, this is done by this parent pointer. Okay, now come to the original code, that the main code of BFS DFS. So, let me erase this. So, this is the main code for DFS. So, what we do here, this is input is the graph, it could be directed or it could be undirected graph, and we have adjacency. This is the input we give, these are the set of vertices, and this is the adjacency list. We give the input as a adjacency list, and we set the parent as null, because this is we haven't started yet. Now, we start with the vertex S. This could be any vertex, arbitrary vertex. We start with a vertex S, and we want to explore all the vertices which are reachable from S, and then we take another vertex. If it is not done, that means this was not reachable from S, then we explore all the vertices which are reachable from that vertex. So, like this. Okay. So, we start with this S, and if S is not explored, excuse me, if S is not explored, that means if S is not in the parent set, then we put the parent of S is null, which we are doing here, and then we call the BFS visit on this S, and this what this will do, this will explore all the vertices which are reachable from S, and this is that same idea. It is follow the path until we stuck, then so after finishing of this code, it will explore all the vertices which are reachable from S. Then we take, after this we take another vertex, and if it is already done, we do not do anything. If it is not done, that means that was not reachable from this starting vertex, then we have to again call the BFS from that vertex. So, this way we complete exploring all the vertices of the graph. Okay. So, this code is basically we explore all the vertices which are reachable from S, and this is the whole code to explore the entire graph. And we have a we have to set the time. This is the starting point of this vertex V when we are calling V, and when we are ending V, this is the finishing time of V, and this time is required for what is called topological search, that is one of the application of this BFS. So, we will come to that. So, let us take a quick example of this code on a graph. So, suppose this is the given graph we want to explore, we want to apply the DFS on this graph. So, A, B, C, D, E, F, and these are the given edges. Okay. It could be directed, undirected graph also. Here we have given the directed graph. Okay. Now, we have to start with a, we want to apply the DFS code. We want to start with a S. So, suppose we start with the alphabetical order A as a S, S1. And now we need to take a vertex which are in the adjacency list of A. So, what are the vertices in the adjacency list of A? B and D. So, we can take either B or D. So, this is a, we take B. So, that is the first edge we see, and the B we check whether it is done or not. So, it is not done. So, parent of A we set as a null, but B is not done. So, we set the parent of B as S. So, that mark we should do. So, parent of B we should set to A. This is the parent pointer, you can see. Okay. Now, again we call the DFS visit on this vertex. Once we call the DFS visit on this vertex, we check all the we have to take a adjacency list of this vertex. So, this is the only vertex which are in the adjacency list of this vertex E. Then we take this edge, and then we take this vertex for the next DFS visit. Okay. And we check whether this is already done. This is not done, and we set the parent of E as B. Okay, this is the parent pointer. And then what are the adjacency list of E? Adjacency list of E is D. So, that is the next number H. Okay, now we call the DFS visit of this vertex. This is the recursive call. Once we do the DFS visit, we check the adjacency list of D. Adjacency list of D is B, but B is this H, but B is already done. So, we do not do anything. We will come back here, that is recursive call, and this has no more adjacency vertices. So, it will go back to the previous vertex. So, that is E, and E has no more adjacency vertex other than D. So, it will go back here. D is also have no more vertex which are adjacency vertex in adjacency list of B other than E. So, it will go back to the vertex A. Now, we check what is there any other adjacency vertex of A? Yes, there is, that is D. So, that is the H number 5, and we check D. D is already marked because the parent pointer of D is set as E. So, D is already in the parent list. So, it is already marked. So, we want to avoid the repetition. So, then we come back here and it is, we check is there any adjacency vertex of A? No, we are done. So, we complete with this vertex A. So, we already explore all the vertices which are reachable from A. Now, we have to take next vertex because we want to explore whole graph. So, next vertex is we can take B, but B is already done. We can check the parent of B is already in the parent list. Then we check C. Now, C is not done. Then we have to call the DFS visit on this source vertex with this source vertex. So, that is the new call of the DFS visit on this vertex. So, in that call, we have to check the adjacency vertex of this. This is one adjacency vertex. Suppose we take that one, and this is the edge number 6, and again we call the DFS visit on this vertex. This is the one vertex, one edge. So, that is the 7 edge, but this is same vertex. So, we go back here and we check whether is there any other vertex which are in the adjacency list of C. Yes, there is E, but E is already in the parent list. So, E is already done. So, we have done with this. So, this is the, so we have already explored all the vertices which are reachable from C. Then we can check D, D is already done, then E, E is already done, then F, F is already. So, basically we are just explore whole graph by this way. Okay. So, this is the DFS traversal. Now, we need to, we want to identify the edges. So, edges are classify the edges, S classification. For example, we want to do the tree edge. There are 4 types of edges: tree edge, forward edge, back edge, and the cross edge. So, these are, if we follow the parent pointer, yeah. So, this is let me bring the, so this is the tree, this is, so if you follow the parent pointer basically, so this is the, so these are basically tree edges. These are tree edges. Okay. If we just follow this will form the tree, and it is a forest because this is disconnect. So, this is a tree edge. Now, what is a forward edge? Now, if you take this edge, now this edge is from A to D, and in the tree structure, this is a descendant of A. So, this is a forward edge, and if you take this edge, now in the tree structure, this is the ancestor of D. So, this is a back edge. Okay. So, and all other edge are the cross edge, like this edge. If we take this edge C and D, this 2 has neither this is an ancestor of E or neither this is a descendant of E. So, this is a cross edge. Similarly, this is also a cross edge. Cross edge is basically which are connecting between this forest in the trees. We will formally define this. So, tree edge is just we form the parent, we follow that, and that will be the tree edge, and this forward edge is to the descendant. So, this is a tree edge, this is the tree basically. Now, if you take this edge, now this is from the previous one to next one. So, this is to the descendant. So, that is the forward edge. And what is the back edge? Back edge means the, so if this is the tree, so this is a ancestor of this node. So, this edge is back edge. Okay. And to compute this back edge forward edge, we can mark the node for the duration when they are on the stack. We are putting the nodes in the stack. So, there only we can mark it. So, this is for a directed graph, and for undirected graph we have only tree edge and the back edge. There is no concept of forward edge. So, for example, so this is a forward edge, these are all tree edge, and this is a back edge because it is going to the ancestor. So, if this is D to B, so B is an ancestor of D, so it is a back edge because this is a tree structure this way. Okay. And these are basically cross edge. Oh, sorry, this is a back edge, and this is the cross edge. Now, if we have so we can take another example, but that is okay. Now, we want to do two application on this. One is, before that we need to analyze this code DFS. What is the time complexity for this code? Okay. Now, DFS visit from source from any vertex, it will take how much time? It will take the summation of the adjacency list of S. So, this is basically, we know this sum is this is coming from handshaking lemma. This is 2E size of E, cardinality of E if it is undirected graph, and or it is E if it is directed graph. But in any case, this is a order of E times, and we are visiting all the vertices. So, that will give us, and this is for all the vertices, that is once, that will give us V times. So, this is basically a order of V plus E, which is linear time, and which is same time complexity as the BFS, which you have seen. Okay. Now, consider we will discuss two application of this code of this search DFS. That application will basically give us from the this is the cycle detection, whether there is any cycle in the graph, and another application will be the topological sort. Okay. So, to detect a cycle in the graph, we have given a undirected graph, or it could be a directed graph. We have given a directed graph. Now, how to detect a cycle in the graph? So, we can use this DFS algorithm, and we will see if there is a back edge in the DFS exploring, when we are exploring and we are classifying the edge. If there is a back edge, then there will be a cycle, and if the graph has a cycle, then there will be a back edge in the DFS code DFS. So, that is the theorem we are going to prove now. So, the theorem is telling, if the graph has a cycle, then the DFS has a back edge, and vice versa. If the DFS has a back edge, then there is a graph there is a cycle in the graph. So, we will prove the one part, this one. If the DFS has a back edge, then there will be cycle in the graph. Another part you can similar. So, suppose this DFS is we have given a graph, we run the DFS, we classify the edges, and there is suppose there is a back edge. Okay. Now, suppose these are the this is the vertices, and these are the tree edge, and there is a back edge, means there will be a edge from any vertex to its ancestor in this tree ordering, tree edge. Okay. And suppose this is the edge, suppose this is the back edge. So, this is the edge from vertex to its ancestor, that is the back edge, and we got one back edge in the DFS when we run the DFS. So, that is a cycle, because this is the cycle. So, that is the prove. And the others, another part which also we can prove, that if the graph has a cycle, then our DFS will report a back edge. Okay. So, now we will see another application which is on job scheduling or the topological search. So, what is a job scheduling? It is telling, given a DAC, directed acyclic graph, say this is a DAC, there is no cycle in the graph, and this is a directed graph. So, directed acyclic graph, no cycle in the graph. You can check there is no cycle in the graph. Okay. And job scheduling means this vertex are represent the tasks, this is the vertex, this is the vertex, and the edges are represent the dependencies. So, the order of the task, so we need to order this task without violating the dependency. So, that means this task will be finished after this. So, we have to order this before this. So, this is the order we are doing by the DFS finishing time. So, DFS finishing time has a role for this. So, we will see this will be basically, this is nothing but a topological ordering, topological sorting of the vertices. So, we want to give a, if we have two vertex, if we have a edge like u to v between two vertex. So, you have a edge u to v. Now, if there is a edge, now whatever value, whatever order of this vertex we give, this vertex order has to be more. So, that means we first do this job, then do, that is the job scheduling applications. So, that will be done by the what is we know as a topological sorting of the vertices. So, just let us recap what we mean by topological sorting. So, basically we need to give the numbering of the vertices, say suppose there are n vertices. So, this vertex should be numbered by 1, 2 up to n, and the numbering will be such that if there is a edge u to v, I mean vertex u to vertex v, say you have a edge between these two vertex u to v, okay. Then whatever number we are giving to this vertex, that is d fu, this is say I, and whatever number we are giving to this vertex, this is fv. So, I must be less than j. So, that is the ordering. So, we must do this job before doing it, because this is dependence. Okay. So, that is the, so this is one example of the topological sorting of the vertices. We can give this vertex number 1, then this is 2, this is 3, this is 4. So, you check any edge, say this edge. So, this is 4, this is 7. So, we have a we are preserving this ordering. So, this is called topological sort of the vertices. So, this we want to do in order to have the job scheduling of that, the vertices are the task and these are the edges are the dependent. So, we must finish this job before this job. Once we, because this job is depend on this job, unless we finish this job we cannot do this job. Okay. So, this is something like function call in the main function in that. So, there are many applications on this. Okay. So, this is a what is called topological sort. Now, how we can do this topological sort on the vertices using the BFS code. So, just recap the BFS code. So, if you remember, we have a start time and finishing time. So, we just look at the finishing time of each vertex, okay, and we record that and we reverse it. If we reverse it, that will give us the topological ordering of the vertices. So, we reverse the DFS finishing time, okay, the time when the vertex V is finishes. So, this is the time. So, if you so this is when V is finishes, that means we already explore all the we explore the path, again we come back here, then we come back. So, that time we will come back the previous vertex, it is finishing that vertex. So, that is the time. So that finishing time we record. We store the finishing time of each of these vertices in the DFS search, and then we reverse this finishing time, and that will give us the topological sorting of the topological ordering of the vertices. Okay. So, we do the DFS visit of a vertex and we order this, and then we order we append the time, and then we reverse the time. Now, why this will give us a question is why this will give us a topological sorting. Consider a edge u to v. So, let us draw this. So, we have a edge, two vertices u and v, and there is a direct edge from u to v. Okay. Now, there are two cases. Case 1 is, there will be two cases. Oh, we have a picture over here. Case 1 is if u visited before v. So, u visited before v. So, if u visited before v, then we take this path at some point of time. There could be another path also. There could be other path also. We can explore that path, then we will come back here. Then we have to take this path in the DFS visit call of u. So, we can take another path, that is fine. We can take this, then we will explore all the way, then come back here, again we come back here, then again we can go the another one, come back here. But at some point of time v is not done, say v is not marked in the parent list. So, at some point of time we must visit v. So, when we visit v, then we must explore all the adjacency vertex of v, then we finish v before u. So, v will be finished first before u, and then we are reversing the order. So, that means, so v is v is finishing first before u. So, then we are reversing the order. So, that means this will take the more number than this. So, that is the idea. Now, the other case is if v visited before u, but that is not possible. If v visited before u, then we have a cycle. We can prove that there is a cycle in the graph, but this is the DAC, directed acyclic graph, but that is not possible. Okay. So, this is the topological sorting of the vertices. We just record the timing, finishing timing of all the vertices, we store it, and then we reverse this timing to get the topological sorting of the vertices. Okay. Now, the question is, so what we cannot do for this DFS, which we can do in BFS, because BFS, wait first search, we did the level by level exploring from a source vertex, and that will give us the shortest path. But here the DFS cannot give us the shortest path. For example, so from this to this vertex, what is the shortest path? This is the shortest path, but DFS is visiting this vertex after all the way to this. So, DFS, the depth first search, will not give us the shortest path, whereas the BFS can give us the shortest path. So, this is the end of this lecture. In this lecture, we have covered graph search, basically to explore the graph, and there are many ways to explore the graph. So, we can explore a graph from a source vertex to all other vertices which are reachable from that vertex, and that is basically our level by level we did in the breadth first search, the BFS first algorithm we have discussed, and there we have seen the BFS can give us the shortest path. Actually, it will give us the shortest path from that source vertex to all other vertices which are reachable from that. And then we have seen many applications of the graph search, like web cloning, then the network broadcasting, and there are many other garbage collection, and then solving the puzzle like Rubik cube we have seen. So if we want to solve the Rubik cube, then we must know the BFS code. So then we can solve the Rubik cube. And then in the second half of this lecture, we have covered the another graph search algorithm, which is called depth first search, to explore all the vertices of the graph. And we have seen two applications of this code, depth first search. One is the cycle detection in the graph, another one is the topological sorting. There are many applications on this, but in this lecture we have discussed two applications.